This is now the fourth episode in our exploration of the mechanical quantities, which are combinations of space, time, and matter. More specifically, we've been focusing on standard mechanical quantities, where the exponents x and y are small integers, such that the quantities can be represented in the table, including many of the common nouns in the vocabulary of mechanics. But there might be more, and we invite you again to suggest additional quantities in the comments with the hashtag #mechanicaltable. This table offers a graphical way to understand the relationships between different mechanical quantities. For instance, in episode 2, we discussed mechanical quantities on the same line, like strength, energy, force, stiffness, stress, and force density. We saw that ratios of mechanical quantities on the same line, any line, produce simple length, which provide a mechanical understanding of the size of things, from astronomical to microscopic scales. From this perspective, a size L is understood as resulting from a balance between two opposing mechanical factors, a quantity Q1 tending to increase the size, and a quantity Q2 tending to shrink it. The size could be large or small, depending on the values of the underlying mechanical factors. In the last episode, we discussed the relationships between mechanical quantities on the same column, like action, energy, and power. We saw that ratios of mechanical quantities on the same column produce simple times, which provide a mechanical understanding for durations, periods, frequencies, and rates. In particular, we mentioned the ratio of action and energy, dear to quantum mechanics, the ratio of energy and power, which dictates how long you can drive on a full tank, as well as the life expectancy of the sun. The ratio of mass and stiffness gives the period of oscillation of the mass and spring system, or of a droplet, or the ratio of viscosity and stress, which is central to rheology. These were just 4 examples out of many possible pairs, but they illustrated the same principle. Time, just as size, can emerge from a balance of two opposing mechanical quantities. Today we're going to talk about quantities on the same diagonals of slope -1, like mass, momentum, and energy. Ratios of these quantities produce simple speeds. Take a first quantity Q1, with space exponent x1 and time exponent y1. Let's highlight the diagonal of slope -1 passing by Q1. If we take a quantity Q2 somewhere along that diagonal, then its exponents, x2 and y2, are constrained by those of Q1. Here, for instance, the exponent x2 is equal to x1 minus 2. Then, since Q2 is on the green diagonal, the time exponent must involve the same gap of 2. More generally, for any difference of column and line n, two quantities on the same diagonal of slope -1 must have dimensions of this form. Then, what would be the dimensions of the ratio of Q1 and Q2? The mass cancels out, of course, but also the length to the power x1 on both sides, and the time to the power y1, leaving only a quantity with dimensions L to the power n and t to the power -n, which we can write as Lt-1 raised to the power n. Moving the exponent n to the other side, we see that we have produced a speed, that is, a distance over time. And if we want, we can express the number n from the difference between the space exponents of the two quantities Q1 and Q2, or from the difference in the time exponents. So, in episode 2 we saw simple length for quantities on the same line, so where the difference in time exponent y2 and y1 is 0. Last episode, we saw simple times, where the difference between x2 and x1 is 0. That is, the quantities are on the same column. We now have a formula for simple speeds, where the ratio between the differences in time and space exponents is -1, so the quantities are on the same diagonal of slope -1. This formula looks identical to the simple length, and just as for the simple length, the numerator is the quantity with the highest space exponent, such that x1 minus x2 is positive. We can also write the formula like that, which looks like the simple time definition. Now the quantity in the numerator is the one with the smallest time exponent. So, for instance, if we consider the mass and the energy, the numerator will be the energy, and the mass will be the denominator. And since the difference in their space and time exponents is 2, the simple speed built from them will have a 1/2 exponent. This first example of simple speed is probably the most well known. The combination of energy and mass produces a speed, which underlines the concept of kinetic energy, and which can be used to derive the speed of projectiles of known mass and energy. The energy, one of the most famous mechanical quantities. Its name comes from the ancient Greek energeia, which means activity. When the concept was formalized in the late 17th century, it was called vis viva, the living force. There are many forms of energy depending on different paths connecting it to other physical quantities. All these different forms are associated with different units. The foot-pound force, the BTU, that is the British thermal unit, the horsepower hour, which, like the kilowatt hour, is related to the connection between energy and power, which produces a timescale, as seen in the last episode. There is also the therm, the calorie, the electron volt, or the ton of TNT, which is the energy released by the explosion of a ton of TNT, something we discussed at length in the explosion series. And there are other units, so much so that we cannot list them all. The standard unit of energy is the joule, which is better suited to our purpose here. Indeed, 1 joule is defined as 1 kilogram meter square per second square, which makes perfect sense if we recall the relative position of mass and energy in the table. We can go from mass to energy by multiplying twice by a distance and dividing twice by a time. So if the mass is expressed in kilogram, then the next cell to the right can be expressed in kilogram meter, then kilogram meter square. Now moving down, we get kilogram meter square per second, and eventually kilogram meter square per second square. Everything checks out. The path we took is of course arbitrary. Here we went first right, then down, but you can also go diagonally, as we had done in the first episode. Isolating the meter per second, a unit of speed, it becomes clear that one way to think of energy is as a mass times the square of a speed. The dimensions of energy can be given from those of a mass and speed. The most famous example of this formula is the most famous formula, the mass-energy equivalence. For any rest mass m, the existence of a maximum speed c, the speed of light, implies an energy E. The mass is a storage of energy, and the conversion of a small mass can produce huge energies, since the speed of light is so large. Another more ancient example of this connection between energy, mass, and speed is the kinetic energy. In this context, the speed v is much smaller than the speed of light. The kinetic energy is then the speed of an object of mass m moving at a speed v. Usually this formula is used to compute the energy from a known mass and speed v. However, the formula can also be rearranged to express the speed from the mass and energy. The mass can be that of a projectile, like a cannonball or a bullet. The mass m is that of the bullet. The energy E comes from the gun, from the explosion in its barrel. In this context, one speaks of the muzzle energy. The speed v of the projectile, or muzzle speed, is then given by the ratio of energy and mass. We can check the validity of this formula by considering an experiment realized by the slow-mo guys, where they fired 4 different guns and measured the speed of the bullets. From the specification of each gun, we can know the masses of the bullets and the muzzle energies, keeping in mind that the actual values may differ a bit from these references. For each shot, we have a mass and an energy, so we can use the formula to predict the speed of each bullet. Here are the results in meter per second. and in miles per hour. The comparison with the measured speed is pretty good. The only significant deviation is for the AK-47, while the speed differs by 7%. But this does not mean that the formula we used is wrong, more probably that the rifle or bullet did not follow the tabulated standards we used. There are many subkinds of AK-47 with slightly different muzzle energies, and the bullets can also vary a bit. This formula can be used to rationalize the speed of all sorts of projectiles. Bullet racing in a straight line, but also debris flying in all directions, as in the case of explosions, small or large, or even astronomical. For instance, in supernova explosions. For some types of supernovae, like this one, the mass and energy are known with some confidence. The mass is that of the progenitor, the exploding star, with a mass around that of the Sun, which is 2×10⁻30 kilograms. And the energy is around 2×10⁴ joules. In this context, the speed of the leading edge of the supernova remnant can be estimated from the ratio of energy and mass. Given the uncertainty on the mass and energy, the factor 2 is a bit pretentious, so it's probably safer to drop it and use an approximate sign. We can then estimate the front speed by plugging the values for E, the energy, and m, the mass, reaching a daunting 10,000 kilometers per second. Well, we've spent quite enough time on this first example of simple speed. We must now move to a different case, involving the ratio of stress sigma and density rho, leading to a mechanical understanding of the sound speed. Our first example involved mass and energy on the same diagonal, 2 lines and 2 columns apart. Density and stress have the same relative position, but further to the left of the table. Density is a mass per unit volume, and stress is an energy per unit volume. This was the simple speed built from the ratio of energy and mass, and this is now the simple speed built from stress and density. No surprise here. This formula describes the speed of sound in materials with a characteristic stress sigma and a density rho. Here, the word sound must be understood quite broadly to encompass propagation in all sorts of materials: solids, liquids, gases, plasmas, not just the sound that we can hear in the air. In this context, the stress sigma is usually understood as an elastic modulus. In episode 2, we gave orders of magnitude for the elastic moduli of different materials. These are just rough estimates, and in practice, the modulus of a material usually depends on the type of deformation, like compression versus shear. There are many ways to classify deformations, and an equally long list of elastic moduli: shear modulus, bulk modulus, Young modulus, P-wave modulus, etc. To each modulus is associated a type of speed. For instance, let's take the Earth's crust as an example. Its density is around 3 tons per cubic meter. For shear waves, the modulus is around 50 gigapascals. So overall, the speed of these waves is around 4 kilometers per second. For P waves, the modulus is around twice bigger, so the wave speed is around 6 kilometers per second. So the P wave, or primary or pressure wave, moves faster than the S wave, or secondary or shear wave. Seismographs can detect the delay between the arrival of the primary and secondary waves. This delay is related to the distance, d, to the epicenter, and to the speeds of the S and P waves. So the distance to the epicenter can be computed. Here it is around 11.4 kilometers away from seismograph A. But we do not know the direction. Adding a second seismograph would leave only 2 possible locations. And you can easily imagine that a third would complete the triangulation. The in-depth analysis of seismic data in the past 100 years has led to our current understanding of not just the Earth's crust, but also its interior. For instance, we know that the Earth's outer core is liquid because S-wave cannot propagate through them, since shear waves are damped in liquids, a topic for another time. In contrast, the P-waves go through, but their deflection informs on changes in density and modulus in the different layers of the Earth, as shown on these GIFs from the Incorporated Research Institution for Seismology. This seismotomography, revealing the structure inside the Earth, is analogous to the sonography, commonly used to image fetuses. In this case, as in many other medical applications, differences in sound speed due to changes in densities and elastic modulus allow to see inside the human body. The formula is the same, but the speed is here much smaller than for earthquakes. The density is close to that of water, so around 1 ton per cubic meter, but the elastic modulus for human tissues is typically around 10 kilopascals, so the speed is around 3 meters per second, far slower than the kilometers per second for seismic waves. The higher the elastic modulus and the lower the density, the higher the speed. This was the sound speed, the simple speed based on density and stress. Let's now consider a new pair, surface tension or stiffness gamma, and viscosity eta. The speed built from these two is called the Visco-capillary speed. Since viscosity and surface tension are next to one another along the diagonal of slope -1, then the simple speed is just a simple ratio, no exponent. We're planning to discuss this speed in detail in the droplet series, so let's only say a few words here. Maybe by the time you're watching this, the videos on droplets are already out. In the previous episode, we mentioned the formation of a drop by pinching. In this example, the fluid was water, and we discussed the fact that the time required for the drop to pinch off was given by the ratio between the mass of the drop m and the surface tension gamma. This is not the case for all fluids. For significantly viscous fluids, the pinching time is not that simple. But the speed at which the necks get thinner is this speed, the visco-capillary speed. The same simple speed also shows up in the spreading or coalescence of viscous drops. We'll talk about that in the droplet series. Time to move on to a different example of simple speed, the one associated with the ratio of force F and friction zeta. This pair gives the characteristic speed in multiple contexts, as for the drift speed in viscous fluids, or in the field of active matter. We just saw viscosity and surface tension next to one another along the diagonal of slope -1. Moving to the right, friction and force are similarly positioned. So the associated simple speed is just F over zeta. The greater the force, the higher the speed, and the greater the friction zeta, the lower the speed. That seems pretty intuitive. One famous example of this speed is in the context of an object falling inside a viscous fluid, like this steel ball in corn syrup. In this context, the impelling force F is the weight of the bead, with m the mass of the bead and g the acceleration of gravity. The friction or drag coefficient zeta can be estimated if we know the weight and the speed. For a ball of steel with a diameter of 1 centimeter, the weight is around 0.04 newtons, and the speed in syrup around 2.6 centimeters per second, which is the ratio of the driving force and the friction, which must then be around 1.5 kilograms per second. In this example of passive sedimentation, the driving force is the known weight, and from the speed we can estimate the friction. But in this formula, the force F need not be the weight. For instance, the standard acceleration of gravity can be superseded by a centrifugal acceleration if the product between the distance r to the axis of rotation and the square of the frequency of rotation omega is larger than g. Centrifugation provides an effective acceleration, which can be orders of magnitude larger than the standard 10 meters per second square. This formula is very useful in biology, chemistry, and physics to understand the separation of objects based on their different sedimentation speeds. And the equation can be rearranged. On the left, the sedimentation speed is divided by the effective acceleration, and this term is sometimes called the sedimentation coefficient, measured in Svedberg, after Theodor Svedberg, the Swedish chemist who got a Nobel Prize for his study of colloids and proteins and the development of the ultracentrifuge. knowing the effective acceleration and measuring the sedimentation speed allows to separate objects based on their mass and friction. By definition, one Svedberg is equal to 10 to the minus 13 seconds. And indeed, a speed divided by an acceleration is a time. The right-hand side reveals that this kinematic ratio of speed and acceleration can also be understood mechanically as a ratio of mass and friction. The sedimentation coefficient is the simple time built from the mass and the friction, a pair on the same column, which we can add to the list of simple times that we started in the last episode. For sedimentation or for centrifugation, the driving force can be expressed as a product between a mass and an acceleration. If we wanted to be a bit more precise, we could also include the effect of buoyancy, which produces an effective mass that can be significantly smaller when the density of the object and surrounding medium are similar. However, the most general formula of this simple speed does not require the force to be connected to any mass. For sedimentation and centrifugation, the force is known. But in recent years, this simple formula has also been used the other way around to estimate the magnitude of an unknown driving force F from a known friction. For instance, in this film showing swimming bacteria, between turning points the bacteria move at a roughly constant speed, around 30 microns per second. From this formula we can obtain an estimate for the driving force F from the speed c if we know the friction zeta. And in viscous fluids, the friction can actually be related to the size of the moving object and to the viscosity of the fluid. How the friction depends on the viscosity of the fluid and the precise shape of the object can be a bit complicated, but a quick look at the table is enough to get the right scaling. Friction and viscosity are on the same line, so they are connected by a length. In the absence of any other relevant mechanical quantity, this length scales with the size of the moving object, and the driving force can be expressed from the viscosity of the ambient fluid eta and from the size L and speed c of the moving object. For swimming E. coli, as in this movie, the speed is around 30 microns per second. The size is around 2 microns, and the surrounding medium is here about 10 times more viscous than water, so eta is around 10 to the minus 2 pascals second, the standard unit of viscosity. Multiplying everything together, we get a force on the order of 10 to the minus 12 newtons, that is on the order of a piconewton. And this is indeed the right order of magnitude, although the prefactors that we've ignored can increase this force to a few tens of piconewtons. The origin of this active motile force is a story for another time. So we've seen 4 examples of simple speeds. The one built from energy and mass, the one from stress and density, stiffness and viscosity, and force and friction. Can you think of other examples? Please let us know in the comments with the hashtag simplespeeds. Now that we've discussed pairs on the same line, or on the same column, or on the same diagonal of slope -1, we are quite ready to tackle the general case. What comes out of the ratio of 2 arbitrary mechanical quantities on this table? And this will be the subject of the next episode.